Assalamualaikum warahmatullahi wabarakatuh, and very good morning again to you all students. So today we meet again for our part 2 of chapter 4 assembly language. So let's just continue from what we have left in the previous video. Okay, so basically in assembly language, why do we need to learn the assembly language? Okay, so why do we need to learn the assembly language? So that we can understand the accessibility to the system hardware. So assembly language basically is useful for implementing system software. So it's also useful for small embedded system applications. So if you're interested in, like, for example, making your own Arduino or Raspberry Pi, you can easily understand them by looking at the assembly language, memory usage, everything. And it saves time, and it's also efficiency, save space and time efficiency. Means that you can understand the sources of program inefficiency, tuning the program performance, and writing compact code. So if you can see, like for example in C programming, so you can only reduce up into an equation, but however in assembly language you can even utilize the memory based on what memory you want to use. So you can limit the memory usage to use only, instead of 4, you can limit it into 2. So writing assembly programs, they give the computer designer the needed deep understanding of the instruction set and how to design them. Okay, so and then to be able to write compilers for higher level language, so we need to be expert with the machine language itself. Assembly program provide this experience. So if, for example, if you are a programmer, you don't know how to utilize your memory, you don't know how to utilize your instructions, so what instruction available, so it kind of limits of what you can do. So if you can understand all of the assembly language, means that you can understand up until the core of your PC for you to program your PC. So other advantages, okay, it shows how the program interfaces with the processor, the OS, and also the basic operating system. So and then basic input output system, sorry. So and then it shows how the data is represented and stored in the memory and also on the external device, like for example your keyboard, your mouse, everything. So and then it clarifies how processor accesses and executes instruction and how instruction access and process data. So and then it clarifies how a program access the external devices as well. So in order to understand the assembly language, you need to first look and understand the register first. So what are the register? So register is basically a small memory usually located inside your processor. So unlike your hard drive, SSD, HDD, okay, so register usually very small. But the advantage of register is that when it's small, it moves very fast as almost as fast as the CPU. So whenever the CPU wants some data, it can change the information inside the register very quick, as similar to the frequency of the CPU itself. Okay, so when you have small, you can do a lot of processing. However, the processing is limited to a certain size. So usually it goes up until 64-bit size at the moment. So and then they are usually used to control the instructions being executed and to handle addressing of the memory and to provide the arithmetic capability. So registers, for example, in Intel processors, basically they can be categorized into 5. Okay, registers based on the processor and the makers of the processor itself. They have different organization that inside the CPU. So a lot the different kind of different purpose of registers sometimes being used inside one CPU, like for example between AMD and Intel itself. So for example, in case of Intel, they have 5 basics. So first one is the segment register, second one is the pointer register, third one is general purpose register, fourth one is the index register, and the fifth one is the flag control register. So each of them have a lot of purpose. Okay, you can look this further even in Wikipedia if you want to look at what kind of register you have in PC. Okay, example, one of the most important register is a flag register that uh, give out information regarding when a process turn out to be the answer is 0 or turn out to be negative or positive, there will be a flag register that stores this information. Okay, so other than that, let's take a look only one example here, which is the general purpose register. So general purpose register is usually we use them for arithmetic, logical, and sometimes moving and loading purposes, loading operations. So these 32-bit registers, okay, they can be used in 3 ways. Okay, so the first one, they are called, okay, as complete 32-bit data register. Okay, and then either they have a lower half of the 32-bit, okay, be used as for 16-bit data registers, okay, and lower and higher half of all the mentioned 16-bit registers can be used as 8-bit data register. Okay, so you can split it whether you want to use it as a whole, or you want to use it as 16-bit, or you can use it as 8-bit, 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 for 8 bits. Okay, so some of these data register, they have specific use in arithmetical operation. Like for example, okay, here a 32-bit register, you have 4 32-bit register here. So the first one, we have the AX, BX, CX, DX. So usually we call it as A, B, C, D. So A as accumulator, B as base, C as counter, D for as data. So A usually is a primary accumulator. So any calculation for most input output from the arithmetic logic unit, the ALU, so they will be based on this register. The process is conducted based on this register. So BX, okay, which is known as the base register, they use for index addressing. So it's used for indexing any memory location inside your random access memory or inside your processor, inside your hard drives. So, and then CX, okay, they are known as the count register. So CX register store the loop count in iterative operation. So like for example, you have, if you're familiar with recursive in programming, like for example, you use for command inside your higher level language C programming, for example. So the loop count is being counted inside the C. And then you have D, data register. They use for the input-output operation to support the accumulator itself. Okay. So let's go ahead with the addressing mode. So usually inside assembly language, you have two things, which is the opcode and the operands. So opcode represent the operation, and then addresses represent the operands. So the inside the address field, okay, which is the address of the operand and also the results. So there are certain number of bits being allocated for these addresses. Okay, so in addressing mode, a technique to addressing mode. Okay, so there are a lot of techniques to identify the address to access the operand. So some of them, in terms of addressing modes, we have, like for example, immediate, direct, indirect, register, indirect, displacement, stacks kind of addressing modes. So let's take a look some of them. So for example, in immediate addressing mode, so immediate addressing mode only occurs when you have an opcode with immediate values. Okay, it's not an address basically, it's an immediate values. So the operand here is 20, in case of this add 20, the operand here is 20, is not an address of any memory location inside your PC. So this one represent add the value of 20 inside the accumulator for any kind of processing. So inside the accumulator, if inside the accumulator they have already a value of 10, so the 20 will be added to the 10 and the result will be 30. So there are no memory reference to fetch the data. This one is fast and they will not interfere with any addressing space or memory space inside your CPU or memory itself. So other than that is direct addressing mode. So for example, direct addressing, they will use an address of an operand inside the assembly language code, inside the assembly language code. So like for example, add A. So means that it adds the content of cell A to the accumulator AC. So the address of A will refer to the memory, like for example in your random access memory, and pick up the information and put it back for the operation. So this one, one memory reference to access the data, no additional calculation to work out. So they use a limited address space for the addressing mode. And then we have the indirect addressing modes. Like for example, in this case, the address that you look up inside your memory is another address for another memory location. Okay, so this one, for example, for operation add A, so the address of A refers to an address of another location inside the memory. So it's a two address. So this one, you need to, the CPU need to do, like, for example, two things at once. Need to refer from the address A and then go towards address B. Okay, so this one is what, it takes a little bit time for the CPU to process in order to look for two items inside the memory itself. Okay, so we look at the three types of addressing modes that I've introduced. And next is about the instruction format. So usually in the instruction set, okay, like example, in the addressing mode, you have an add 20, add A, add B, okay. So inside the instruction format, they have an operation code and they have certain number of operand you can use inside the instruction set. Okay, so the operation of CPU basically determined by the instruction it executes. So the CPU instruction set is the collection of different instructions that CPU can execute. So each instruction must contain the information required by the CPU for execution of the operation code, the source operand reference, the result operand reference, and the next instruction reference. Okay, so next instruction reference usually the next line of your coding. If first you want to use add 20 and then subtract B. Okay, so the next line of the coding is the next instruction reference. So the operands, usually the main or the virtual memory inside your PC, a CPU register, or any input-output device available in your PC. Okay, it's not efficient to put all the information required by the CPU in a machine instruction. So each instruction is represented by a sequence of bits, okay, which is divided into two fields, the opcode and the address. And the processing becomes faster if all information required by the CPU in one instruction or one instruction format. So like for example, in this case, you have one opcode, address of operand 1, address for operand 2, address for result, and address for the next instruction. So the problem is that if you look at this kind of operation, this kind of instruction, the instruction is long, okay, certain bits size, okay, takes a few words in main memory to store one instruction. So the solution to provide a few instruction formats, like for example, instead of having 3 memory address location or 4 memory address location, you can have either only 1, 2, or 3, or depending on the addressing mode. So instruction format with 2 address is usually being used by the Intel processors. So let's take a look at the opcodes, common opcode represent here. Okay, these are 5 mnemonics that you have here for addition, subtract, divide, load, and store. Load means load data from the memory. Store means store data from to a memory location. So let's take a look at a longer instruction code which is based on 3 address. So 3 address, here you have the first one, address of result, and then you have operand 1 and operand 2. So let's take a look at that. You want to do an operation of y equal a subtract with b. So this one, the code will be sub y a b. Result will be in y, operand 1 is a, and operand 2 is b. And the operation involved is subtraction. Okay, so address for next instruction, okay, will be inside the programming counter itself. And then you have the instruction for 2 address. So instruction for 2 address, they don't have, they have the operand 1 and result as the same place, same location. Like for example, in this case, y equal y subtract with b, the code for it is sub yb. Means that operand 1 is y, operand 2 is b, and the result will replace to the operand 1. Okay, and the address for the next instruction need to be referred to the program counter. And then finally, you have an opcode that use only one operand. Okay, operand 2 means that you have a register inside your CPU that operates that's like a table. Okay, that's like a table, and you just add things to the table based on the instruction. And for example, you have empty table, and then you load A into your table, and your table now has A, and then you add B to the table, means that the A will be added with B, okay, or subtract with B. So the table is what we call the accumulator. So the AC is the table, okay, accumulator. So this is where the operand 1 and the result is, okay, it's a register. So at the end of the operation, you need to save the data inside the accumulator into a memory location, or it will be erased and used for next instruction, okay, or be changed for in case of anything. Okay, so this is a short instruction, okay, but they need a lot of this instruction. So instead of, if you have 4 instruction using 3 operands, using 1 operand you might have up until 12 or 15. Depends on the type of code itself. So example of 3 instruction here, okay, you have here y equal a minus b. It works like a common mathematics, okay, common mathematics. You have to do the equation, okay, the equation, you can convert the equation into the code like the mathematical process, where you have to do the multiply and the divide first, okay, and then the bracket. I basically do the bracket first. Inside the bracket, you do the multiply and the division first, and then finally conduct with subtraction and addition. So in this case, if you look at this case, you can see that where can we start first. So in this case, we start with a minus b. So a minus b sub y, ab means that a minus b, the data is being stored in y, register y. And then multiply TDE. So they do the TDE first, the DE first, D times E. So the data is being stored in T. So they do not add the C plus D. Why? Because D times E is a more priority in mathematics instead of C plus D. Okay, so do the D times E first. And then next, add the T result in T with the C. Means that after D times E, you add with the C. And this data being stored in register T. And at the end, inside the register Y, you divide content of register Y with the data from register T and store the result in register Y. So you get the whole results of this equation inside your register Y. So next is another example, the same example, but this time we are using two instructions. So in this case, you have move YA sub YB. Move YA means that put A inside register Y. And then sub YB, the content inside register Y, you subtract with B. And then you have move TD. Okay, you put in data from D into T, multiply it with E, add with C, and then finally you divide the Y with T. And the data will automatically save in Y, because Y is also, the first operand is also the result operand in this case. And finally, this one is for the one instruction. So the code is here. So basically what they do is that load D into the accumulator, multiply with E inside the accumulator. So accumulator now has accumulator times E, and then D times E, and then add C to the accumulator. So now we have completed this instruction. Okay, so and then you have to store it into Y first, because next we're going to do this instruction. So and then load A into the accumulator, subtract it with B inside the accumulator, you got this result inside accumulator. Now you divide it with the content in register Y, where you have stored the C plus D times E before. Okay, divide it with Y. Okay, you got the result in the accumulator, and you transfer it inside the register Y. Okay. So there are 3 kinds of addresses that you can, addresses mode that you have inside your assembly language. It depends the number of addressing mode. It depends on the maker of the component itself, based on the operating system itself. Okay, and this is basically the content of the assembly language that you need to learn for the basics. Okay, so that's all for today from me. Thank you very much for staying with me for the next chapter of the computer architecture organization. So I see you guys in our future content, chapter 5. So thank you for the subscription and thank you for the likes for the video. Hopefully I can see you again in my next video. Thank you very much. So stay safe, stay healthy. Bye bye. Assalamualaikum.